what's the census on retaking, everybody? Are we retaking?
That's up to you guys.
Yeah. Nobody? I want to, kinda, sorta.
I am.
Yeah, okay. Alright, okay. And I'll be there too. We can do it. Yes.
Alright, so today we're still gonna hang out with this idea of vector value functions. I really wanna hang around specifically this idea of particle motion, talking about velocity, acceleration, speed, things like that. So we have a particle moves around in 3 dimensions, and careful, it says with velocity components. So this already is the first derivative. It also could have been presented as you have a velocity vector value function as x of t, y of t, z of t. So it could have said that this is your velocity. And it would not have meant anything different.
So how do you know that it's like our first derivative? Just because it says the dimensions of
The velocity. It would have said position if it was the original. Now I am given something about the position. This, if you want to mark this in your notes, this is the initial condition. And really the only hard part of today's lesson is calling back to Calc 1, Calc 2, and how we did these problems before. But you're going to be given an initial condition, and you have that x of 1 is 3, y of 1 is -1, and z of 1 is 2. So if you want to write that just to kind of convince yourself exactly what that is saying.
So you write that in, no, let me be quiet. Okay. Parametric time. Okay.
Part A says write the components of the velocity vector at t equals 1. So when it says components, we essentially want to write the velocity vector at 1. So we're going to have I want a way of writing like derivative. Let's go ahead and call this like x prime, y prime, z prime. Just some notation to show that these are the derivatives of each of the components. So the velocity vector is going to be x prime of 1, y prime of 1, z prime of 1. And don't forget, that's what we were given when we first started. So x prime of 1, 2 times 1 is 2, minus 2 is 0. Y prime of 1 is just 2. And z prime of 1 is 1 squared minus 1 is 0. So let's make sense of this answer here. This is a velocity vector. This is saying at t equals 1, I am not changing in the x direction. I am increasing in the positive y direction. I'm not moving at all in the z direction.
Okay.
So if you want to think of the kind of geometry from unit 1, that means that this is moving perpendicular to the xz plane. So it's moving straight up in that y direction. Questions?
At think that it's kind of cool. It's like it's flying around and it's just.
At that moment.
Yeah. It's cool.
The next part, determine the speed of the particle at t equals 1. So think back to both Calc 1, think back to physics. What does speed mean?
Is it also velocity?
See?
Is it also velocity?
It has a lot to do with the velocity.
Is it like the velocity out one direction?
See?
It's just not the direction, it's just.
Yes, exactly. So in Calc 1, one-dimensional things, we would say it's the absolute value of velocity. So it doesn't matter if you're moving forwards or backwards, it's just the speed, we don't care about the direction. But how can I find that from a vector?
Vector. You gotta take the antiderivative, or I forget what it's called. Did you going back?
Is it
I guess not.
The what?
Direction? No, not the direction.
It's not the
Magnitude?
direction, it's the magnitude.
Yeah.
Magnitude.
So just mark this down in your notes. When it asks for the speed, and you're given a vector, it's the length of the vector, or the magnitude. So I have a velocity vector at t equals 1, nice. So if I want the speed, you just want the magnitude
So it's gonna be
of that velocity vector at t equals 1.
let's go to let's do 2. Speed 2. Okay. Does it have any units, so it's just 2?
So if we were given units here, and this was in like, inches per second or feet per second, the speed would keep the same units.
Okay.
The only thing different, speed, velocity, is I'm not caring about a direction.
That's right. Exactly.
So thinking about what this is saying, it's like if I'm moving 2 feet per second in the x direction, 3 feet per second in the y direction, maybe 1 foot per second in the z direction, well, you're traveling all of that at once, so one vector. So the magnitude is the speed combining all 3 of those. Next one says, write an equation of the line tangent to the path of the particle at t equals 1. So we're writing the equation of the line. I turn on my exam 1 brain. Okay, that's right. We need a point, but now not a slope. We need a direction vector. So it says that it needs to be tangent to the path of the particle. That means the position.
Tangent to the path.
Say it.
Are we using,
This one.
are we using that?
So this is the point. But what is this in this part over here? It's the slope or the direction vector.
Slope.
So we can call this whatever we want. I'll call this T of T. Lastly, I will combine these together.
Okay.
So we're just going to draw a 2D example, remind us what we did in Calc 1 with these tangent lines. So once we've made tangent lines, then our Calc 1 brain, one of the first things that we were able to do is then use this line to approximate values on the original function nearby. So once you have a line, you can plug in a point right next door on the line, and it just approximates what's happening on your original curve. So taking a step back over here, I don't know what the actual position of this particle is. I only know its position at one point and the direction that it's traveling at that one point. So now let's make a new part that says, now use your tangent line Now that you've made a tangent line that approximates the direction that this thing travels in, now use your tangent line to approximate the position at t equals 1.2. This position function that we've created now approximates the original position of this particle, but only at t equals 1. So if I want to plug in a point right next door, like t equals 1.2, I'm going to use s for my position. So I'm going to say the position at 1.2 is going to be approximately whatever I get when I plug 1.2 into this vector value function down there. So looking at the direction vector that we found, we said that this is increasing only in the positive y direction. So it should make sense that our approximation is going to be maybe increasing a little bit in the positive y direction. Where's our original point? Yep. So if I'm increasing a little bit in the positive y direction, the x and the z are going to stay the same. Just an approximation, it's not going to be exact.
Right.
So this is going to be a new idea that we really want to get in the habit of today. You can make it an equation of a tangent line. It's just exam 1, techniques and skills. But then what we're interested in with part 2 is then use that line to approximate values nearby. Alright, we need a new formula for today.
Arc length. Do we really?
So with this question, how big a percentage of the tax
Let's see.
And really what it would be, is it would be something like, you know, given this prompt, and maybe you're just asked only one of those things. Like, given this information, determine the speed. Given this information, write an equation with a line team. So the next thing we have is arc length. So we actually saw arc length in Calc 2, but we just had a one-dimensional thing. But now if you have some sort of path that's being traced out in 3 dimensions, then you can find the length of the curve between the two values. Now, we're going to look between two values of t. So I'm going to find the length of this curve from t equals a to t equals b. So just glancing at our arc length formula, the things that we need are t equals a and t equals b. And it looks like we just need the derivatives of each of the components. X prime of t, y prime of t, z prime of t. Glancing over there, I was already given the first derivatives. If you weren't, you would just take 2 seconds and find x prime, find y prime, find z prime. So this could just ask something as straightforward as, oh, you know, find the length of the curve from t equals 0 to t equals 6, something like that. Or, if it's in a word problem like this, and it's talking about velocity acceleration, then you could think of this as the distance traveled. So the arc length is going to be the distance that this particle flying around in space travels from t equals a to t equals b. So let's dress it up like that.
What's the other way you can ask it, like the easier way?
Find the arc length,
I was just gonna type.
or the length of the curve. So I want the definite integral from 0 to 6. Then I want the square root of x prime, 2t minus 2, squared, plus y prime, which is 2 squared, plus z prime, which is t squared minus 1 squared. I would just mark it in your notes right now. These are very rarely able to be solved by hand. I can maybe think of an example where I can get this to work out nice and cleanly and we can do a normal Calc 2 integration. Otherwise, we need graphic technology. So go ahead and open up Desmos. So I'm pulling up Desmos 3D. It really doesn't matter if you use 3D or 2D. So just to remind us to do integrals on the calculator, you can type INT. The second that you hit T, it auto-populates a definite integral. I want the definite integral from 0 to 6. For square roots, you can type SQRT. The second you type T, auto-populates. And then you can just type it in as you see it. Desmos will not give you an answer at first, and then you realize, oh, that's right, I need to do T. So if you guys are thinking about, an exam question here, maybe it can very easily appear in the multiple choice section, but maybe the question says something like, find the distance traveled by the particle from t equals 0 to t equals 6, write, but do not evaluate the integral. And then you would just choose the answer choice, which integral represents the distance, but maybe doesn't give you a decimal approximation. If it's a free response, then it would say something like, round your answer to the nearest 1,000. And then you would throw this at Desmos, get a number, write it. Questions there? I'm going to come back over here. Am I good to close Desmos? Do you have any questions on the calculator? So now determine S of t, the particle's position at time t. Yep, you're just going to integrate. Don't forget, you're going to get a plus c. That's why this initial condition is going to become a thing. I know that at t equals 1, when you plug in 1 for t, you should get 3 for x. After you've integrated the y component, you know that when you plug in 1 for t, you should get negative 1 for y.
So you just plug in that first one that they give you for the coding.
You're going to get a C1, C2, C3. You're going to plug in t equals 1,
Alright.
set the x equals a 3, y equals negative 1, and then solve for C1, C2, C3. I'm going to give you guys a couple minutes head start.
Okay.
See you. Oh, sorry, I passed it.
Oh, is that? Oh, I see. 2, 3, and 2, 3.
Sorry, we got it. tired. It's okay. It's okay.
It's like I was constantly traveling for 4 days because I had to go 20 hours on an airplane, like to get home, including layovers and driving time. And then after that, I get like almost no sleep, and then traveling all the next day for the wedding, and we're at the wedding, and then traveling after the wedding to get home, and then get to the airport, and then airport.
Yes, yes, I
Oh,
know.
plug-in lines.
We understand.
Oh, so the traffic.
At times, that's the only thing I don't. Wait, why are we plugging in one and then two?
Same.
Why are we plugging in one?
So, well, you integrate first, right?
Yeah.
So now you know it needs to be true that when you plug one in for t, the x coordinate is 3.
Can it be any number or does it have to be?
Well, this couldn't have been any number.
Okay.
You're gonna use t equals 1 since that's what we're doing. So once you've taken the antiderivative of each of the components, you have an x of t, a y of t, a z of t. They're not finished yet because now you have a plus c for each of them. And again, be careful, it's not necessarily the same c. So maybe you can call it C1, C2, C3. If you want to call it plus A, plus B, plus C, sure. As long as you recognize that you've got a constant at the end that are not all necessarily the same. We know that when we plug 1 in for t, the x coordinate should be 3. That was the note that I made to myself in the beginning. When you plug 1 in for t, you get 3 for x. When you plug 1 in for t into the y, you should get -1. And when you plug 1 into the z, you should get 2. So in this step, when I plugged in 1, we could have been normal people and then just combined fractions. I personally just avoid it. I just multiply the entire equation by 3 and then just ran with that. You'll get the same answer if you combine, fractions. This is my final answer yet though. This is only finding the constant C1, C2, C3. Very last thing now, don't forget, we just have to plug it back in. So now I can say my position function is t squared minus 2t plus c1, yes, but we found c1 to be 4. Then we have 2t plus my c2 is negative 3. So you could just say minus 3. And lastly, t to the third over 3 minus t plus 8. Questions? Alright, let's do one more thing. Say it. Would definitely. It's just Calc 1, Calc 2, we're just gonna do 3 different things. So the next thing I want to show you here is you won't necessarily always have a nice function that you can just simply take the antiderivative of, use your gateway techniques, and solve for C. Maybe x prime of t is given to us graphically. Maybe x prime of t is given to us like it was over here, but maybe this thing you can't actually find the antiderivative by hand. It's not just a nice Calc 2 problem. So I want to make sure that conceptually we still understand kind of how we can do problems like this. So this is an initial condition. This is saying x of 4 equals 6. This is the graph of x prime, the derivative. The goal is to find x of 0. So a couple ways you could think about this. I like to think of x of 0 as being where I was at t equals 4, I'm going to put t equals 4 just so it's emphasized here. At t equals 4, you were at 6. Plus, how much did you change from t equals 4 to t equals 0? If we're not fully convinced there, then you could say x prime of t from 0 to 4. Thinking back to Calc 1, isn't that then fundamental theorem of calculus, x of 4 minus x of 0? So if I want to solve for x of 0, I can subtract the x of 4 from both sides. And if we're like, oh, hang on, those look a little different. Don't forget, we have this property that says you're allowed to switch the limits of integration and change the sign. So we might be off by some negatives and some positives, and we can find ways of rearranging this, but you would get the same. I think once this is solidified in your head as to why this works, you're like, okay, I'm just going to run with this every time. If not, being able to kind of write it from your fundamental theorem and being able to just rearrange it will work too. So, x of 0 is going to be 6 minus the definite integral from 0 to 4. Don't forget, if you're given a graph of x prime, then the definite integral represents the area bounded between the curve and the x-axis on that interval. So my integral from 0 to 2 is a rectangle with a width of 2, height of 4. 2 times 4 is 8. From 2 to 4, that's a triangle with a base of 2, a height of 4. 2 times 4 is 8, divided by 2 is 4. So that means that the definite integral from 0 to 4 is 12. See? So I want to show you over here that we should get the same thing. So I have the definite integral from 0 to 4 of x prime of t is going to be x of 4 minus x of 0. I know x of 4 is 6. So if you just wanted to make a substitution from the beginning, and you could say, oh, that's just going to be 6 minus x of 0. I could subtract 6 over. Multiply both sides by a negative. and then you still land on the standing statement. We all had different people for Calc 1, Calc 2, so maybe we saw it in different ways. We don't seem convinced, so we're going to do one more. So this says, given y prime of t equals e to the t squared minus 4, and y of 0 equals 2. So you're given a derivative, you're given an initial condition, calculate y of 3. So 2 schools of thought here. I'm going to think that y of 3 is going to be wherever I started plus how much did I change from t equals 0 to t equals 3. You think back to Calc 1, I'm like, okay, that's right. The idea of the definite integral was it represented net change. So if I want to show how much I've changed, that's your definite integral from 0 to 3. If you want to look at this and go, oh, well, I've got y of 0, y of 3, so I can do the definite integral from 0 to 3. And the fundamental theorem of calculus says that is y of 3 minus y of 0. Y of 0 is given to me as 2. Therefore, I could say y of 3 equals 2 plus the definite integral from 0 to 3. However you want to get there, just personal preference. All I'm doing now is just substituting y prime as the formula that we have. And you could look at this and go, okay, well this is easy. You take the antiderivative, but then we land on e to the t squared. There is no use of. There's no integration by parts. There's no manipulation. There's no way to find the antiderivative of e to the t squared. This is not something we can do by hand. When that happens, you plug it into Desmos. So now I'm going to open up Desmos. I've got 2 plus the definite integral from 0 to 3 e to the t squared minus 4 dt.
minus 4 something like that.
We're typing it in, or we all get the same thing? Alright, let's do one last problem type. Just because earlier I mentioned looking at that Berkman formula, I said maybe you could think of a formula that works and you could actually do it by hand. The rest you need a calculator. Let's do one by hand, just so that once you've seen it, you realize like, oh, that's how those are gonna work.
No, it's not. Here we go now.
So by hand, compute the arc length. I'm just glancing over to the right at my arc length formula. Okay, that's right, so it's a definite integral. I've got a square root. But notice it's x prime, y prime, z prime. So maybe just take 2 seconds and actually just compute your x prime, y prime, and z prime.
Oh. Negative sine t, 0 cosine t.
Let's make this a little more exciting. Call that 8t in the middle. So you get an 8 here.
Can you do it? Hold it by hand though.
So we're looking at this one and like, well, he said do it by hand, but how on earth am I going to do this by hand? Yep. Sine squared t plus cosine squared t is equal to 1.
1. Okay. Nice.
And honestly, once you've seen that, you won't unsee it now. Any problem where they try to ask you to do it by hand, it's just a clever way of getting you to put sine squared t plus cosine squared t, and it just cancels out. Or I shouldn't say cancels out, but it just reduces to 1.
So what did we do at square root of 65?
I have all the confidence in you guys that you can finish it from there. I'll give you guys a 30-second head start.
No, I'm not sleepy.
Yeah, so let's find a way of kind of generalizing this idea over here. So if you have f of a equals b and f prime of x and f of whatever you want to call it, m, is going to be the y all the way up to the m value. Hang on. It'll be b plus the definite integral from a to m of f. So I do have practice problems coming around. As well as a project. And one of the things I'll probably try to do is make a tab on Blackboard that's a review of Calc 1 tab. Like, it's been a while since I've seen Calc 1 and I need a refresher. So I'll probably make like a, hey, these are the ideas that are coming back to haunt us. In case you need it, I'll have a tab. So just glancing at those arc length problems, it says find the arc length of the curve from the given interval. Express your answer as a decimal rounded to the nearest hundredth. That is the clear signal to you. Throw it into decimals. Don't try to do it like square root of 2 times 2.
I'm good. No prime, right? So it's raised to 1/2. 2 raised to 1/2. E to T is E to T. What is square and square root? So this be 2T. Yeah.
Because the derivative of this is just going to. Yeah.
So for the first one, we can take the derivative of each of the components. Why? Because glancing over at our arc length formula, this should be 0. Glancing over at our arc length formula, it's the derivative of each of the components squared. So we'll have to remember a little bit of Calc 1 derivative rules. For instance, the derivative of e to the negative t, that's a chain rule. The derivative of e to the negative t is e to the negative t times the derivative of the exponent, which is -1. Now, this one asked me to just express it as a decimal, so once I've done that, I can type it in exactly like this, throw it at Desmos, get an answer. However, just in case, say it was multiple choice, maybe there was one line where they just simplified this. E to the t squared is e to the 2t. The square root of 2 squared is just 2. And e to the negative t times e to the negative t, negative times negative is positive. The negative t plus the negative t is -2. So again, this is just in case it's multiple choice, it says which of the following integrals represents the arc length from 0 to 1. So 0 to 2.
I'm just, I think it's just total for derivative.
Number 3, that should be an interval 0 to 5, not 1 to 8.
Which would give me what as a decimal?
160. 10.
It should be so. It's all of 14.
E-T. That's not
So
correct.
it's- You squared the 2 to get 4, but you didn't square the 7 to get 7. I missed the square on this one.
Yeah, 3t squared.
Yes, you're supposed to square everything, so you get -2 squared is 4, and then sine squared.
Over T.
Does that change our decimal? Or the 160 is with
Yeah.
the square?
160.
Yeah, 160.
Squared.
And then also on part
160 is
A,
good.
the 3t squared should be squared also on the inside. dy dt on that.
9.
So one more time?
So right there, it's 3t squared, it should also be that on the inside.
3t squared squared.
Yeah,
3 squared. 2 squared.
yeah, 72.847.
One more time?
72.847.
Squared 9.
Okay, let's just quickly glance over the project, just so we have a head start. So a mosquito moves in three-dimensional space between 0 and 20. The position vector is given by x of t, y of t, z of t. We're given that at t equals 0, the mosquito is located at 2, 1, 4. That's our initial condition. And let's just take a glance at what we're given. We're given a formula for x prime, a graph of y prime, and the actual graph of z of t. So these are three independent functions, kind of really making sure that we understand this parametric idea. X of t is going to be its own equation. Y of t is its own equation or graph. Now I'm just given the graph of y prime. So just really exercising, do we know how these work conceptually? Find the unit tangent vector, find the position, distance travel, things like that. All right, when we come in Wednesday, we're going to leave this idea of vector value functions and start looking towards other coordinate systems like cylindrical coordinates and orbital coordinates. In case you didn't see a Blackboard announcement, you will have a chance to retake the exam, exam 1 on Friday. That'll just be right after class. We'll go find a place to sit, take the exam. It's not going to be anything crazy. It's just going to be another popcorn shuffle. Nothing added, nothing taken away. Sound good?
But if we do the redo, then the final will replace the low.
Yes, which is basically your promise to me that it's not going to get worse than that.
Hold on. Say
Oh, my
that
bad.
again. Say that again, what I missed.
Oh, no. If you do the retake,
Uh-huh.
then the final won't replace your lowest test grade. Because that is
Yeah.
replacing your lowest test grade.
Okay.
What I was saying is it's a promise to me that it won't get lower.
Right, okay. That's a serious promise.
More time. From 1:15 to 2.
Every day?
Today, and then Wednesday I'll be in a lot longer, probably from 11 to 2. But send me an email and I'll give you a more exact time as we get closer.